Hi everyone, thanks for coming. We're very excited to be here, at AOL Platforms and share what we've been doing with real-time bidding with Erlang. First few words about me. I started my career back in '95 on this system here. So I was at Ericsson working on the XE10. It was a system that had message passing, a trace system, and hot code loading. So sounds familiar to most of you? In fact, the trace system was so good on this here that in my department, if you were writing bugs on the software, you couldn't submit your bug report until you'd included the solution, which you'd also hot loaded onto the system just to test it. Things changed a little bit. 2004, we moved on to a new platform for 3G radio access. It was a nice step forward for developers to be using C++, but for testers, it was a different story. And I can remember the day a system tester came up to me and said, this thing is just a big PC now. And what he meant by that was if it crashed or if there was some sort of bug, all he could do is take log files, send them to a developer, and hope that maybe 1 or 2 days he will get a fix. 2009 then, I got to do a course on distributed systems. The practical exercises for the course were done in Erlang. I hadn't done any functional programming before. I hadn't seen Erlang before. So it was quite interesting for me. And at the end of that week, I was very frustrated with all the commas and full stops that I couldn't get my head around. But I kept coming back to it because it just looked like an interesting paradigm. And eventually, yes, I really started to enjoy programming it. So this led me then in 2012, I applied for a job at AOL to work on an Erlang system. And the Erlang system was a real-time bidding exchange, which I'll talk about. So this is the office in Dublin. And as you can see, the Erlang developers get the best view there. So be very welcome to come and look. The agenda today then, I'll talk about what is real-time bidding. We'll have a look at the real-time bidding exchange architecture. We're going to look at some bottlenecks that we find in our system. We also look at how we traced and debugged the system. So first of all, what is real-time bidding? We're all familiar. We go onto the internet, and we enjoy reading lots of different articles. And this is a web page from Engadget, and there's a nice article about Lego's new game that they're going to launch. And we get all this content for free, but it does cost somebody to put content up there. And we're all familiar that this gets paid for with advertising. So in this publisher's web page, they have some HTML inserted called a placement. And the placement is just a part of the page where an advertiser can display a banner, such as this ad from Verizon. Traditionally, there's been upfront agreements between publishers and advertisers. And what that means is the publisher knows in advance which advertisers can place ads on their system. With real-time bidding is the buying and selling of advertisements in real time when a page is actually loading in your browser. So a publisher's web page will connect to a supply-side platform. That's where the real-time bidding exchange sits. It's called SSP in this diagram. The SSP then contacts a number of DSPs, or demand-side platforms. The advertisers bid in through demand-side platforms. If they bid in and hopefully win a real-time bidding auction. And the prize for winning the auction is that they get their advertisement displayed on the user's web browser. We'll look at some of the components involved in doing real-time bidding in our system. So as I've mentioned, the user is loading up a web page in their browser. They get the HTML downloaded from the web server, and that includes an HTTP request to our ad server. Our ad server is then going to decide, is this publisher enabled for real-time bidding or not? And if that's the case, a request is made out to the RTB Exchange. The RTB Exchange then decides which DSPs should be allowed to take part in this auction. So the RTB Exchange sends requests off to DSPs, and those DSPs bid into the system, as I mentioned earlier. The winner is chosen, the response gets sent back to the ad server, and eventually a JavaScript snippet is inserted into the user's web browser. That JavaScript snippet then triggers a request off to an advertiser's content delivery network, and we get the ad eventually displayed back into the user's web browser. So I'm going to take a look at the architecture of the real-time bidding exchange. So as I've said, there's a connection between our ad server, which is C++ component, and the RTB exchange, which is done in Erlang. The ad server will send thrift-encoded messages over a ZMQ interface, and they're handled by this ZMQ process in the RTB exchange. For every request we receive, we will then spawn off an auction process. So we'll have at least hundreds of these auctions ongoing concurrently in the system at any one time. The auction process then needs to look up campaign data associated with that request. Campaign data contains things such as floor prices for the DSPs and the supported banner sizes which can be displayed in the publisher's web page. It'll also have things like whitelists and blacklists of advertisers that can or cannot be displayed in the publisher's web page. So all this campaign information gets loaded up into ETS tables when the system starts up, and it's kept up to date the whole time the system is running. Let's take a look at the architecture for actually loading up configuration data. Campaign information is stored as JSON documents, and those JSON documents get appended into tables in a MySQL database. The MySQL database is actually a cluster, so we replicate this data for redundancy and also for load balancing. So as you see in this picture, the idea is that each real-time bidding exchange should connect to a MySQL server in such a way that they're load balanced equally across the cluster. We don't have any load balancer there, so what actually happens is we look up the host name for the MySQL cluster in DNS, and that host name is mapping to multiple IP addresses. So all the RTB exchange has to do is decide which IP address is it that it should use. To do that, we use a function called hashname. What you can see in hashname is that it takes the name of the node that we're running on and a list of those IP addresses for the MySQL hosts. In line 2, we convert that node name from an atom into a list, and then we just sum up that list to get an integer value called sum. In line 3, we calculate an index by just taking the modulus of sum divided by the length of hosts, and then when we index into that list of MySQL hosts, using index, we get the correct MySQL host to connect to. We could also do this if we just took the IP address of the host that we're running on, but we can't guarantee our RTB exchange nodes' IP addresses will increment sequentially. But we do know the node names contain 001 for the first one, 002 for the second one, and so forth. So back to the workflow here. Once we have taken the campaign information, we then contact a Couchbase server to get user mapping information. So when we get a request in from a user's web browser, it contains a cookie for our domain. But when we send requests out to demand partners, we need to include the cookies for their domains. So Couchbase is doing this mapping between our cookies and their cookies. When we have all our campaign information and our cookie information, we then decide which demand partners can take part in an auction. For each demand partner, we will spawn a new process called the DSP process. The DSP process is then in charge of building a request to send to the external DSP using a protocol that DSP understands. In most cases, DSP supports OpenRTB. They might support different versions. And then in other cases, there are DSPs that don't support OpenRTB, but use their own bespoke protocol. the message is sent out with a HTTP request over a long-lived HTTP connection. To handle the connections, we have an application called LHTTPC, and it contains a pool of sockets for each demand partner. So when a DSP wants to send a request, it takes a socket from that pool. It handles one request from that socket, and then when it's finished, the socket goes back into the pool. Having a pool of sockets like this means each DSP gets guaranteed a certain amount of bandwidth. If one DSP happens to be very slow, then we will eventually run out of sockets in that pool, and they won't get as many requests until they can recover from that problem that they might have. So as well as performing all the auctions that are going on, we have a web interface running on this that gives us configuration information and gives us our stats in real time. We are exporting stats to an SNMP file. We have a server taking in those SNMP values, Zenus, which will alert on the system if it needs to. We also use Folsomite then for very fine-grained statistics. So Folsomite is collecting stats on the Erlang VM and also collecting very detailed timer information on each different part of the system and recording a lot more counter values also. And then on top of that, we are taking the creatives that we receive back from the demand partners. We're storing those in a database, and we're sending them off for a third party to scan for things like malware and information about the advertiser. And all that information gets fed back into the auction process. So how much did a system like this scale? So typically, running at peak, a system like this can handle around 8,000 HTTP requests to our demand partners. So it's building and sending 8,000 HTTP requests per second. There are over 1 million placements in the system, so that's over 1 million different placements where ads can be displayed on the internet. And in a day, globally, we would typically send out around 50 billion DSP requests. And that's growing at quite a substantial rate, so I think when we look next month, we'll see these figures are probably a little bit out of date. So what I think we can see from this architecture is that it is a highly concurrent system. We're kind of lucky that all the requests coming in are very independent, and they're not influenced by other requests coming in. It means our auction processes are all very independent from each other. If anything goes wrong with one auction process, it can't affect any other auction going on in the system. And then for the DSP processes, they can all run independently as well and can't affect each other. However, when we do have a concurrent system like this, there are, of course, shared resources. And where we have shared resources, those shared resources become bottlenecks. So what I'm going to look at is what are the bottlenecks that we find in the system when we went into production. I should have mentioned earlier that this product went officially live in October 2013, which is less than 2 years ago. But it was handling some production traffic some months before that. But it's running a very fast growth, and yes, we found some issues that hit us that we weren't expecting. So the first bottleneck I'll talk about is the ZMQ interface. So as I've said earlier, the ad server is connecting to this RTB Exchange over a ZMQ interface. In reality, there's lots of ad servers connected to the RTB Exchange. And then similarly, these RTB Exchange nodes are connected back to all these ad servers. ZMQ with its router dealer pattern gives us this flexibility here. And we can take out an RTB Exchange node, and ZMQ and the ad servers will load balance all those requests among the remaining RTB Exchange nodes which are there. And this was working very well for us for the first few months until we hit our first issue. And when we hit the issue, it looked like this. The top line in this chart represents our requests, and then you can see it was kind of handling them okay, but then it just suddenly dropped off close to zero for about 1.5 hours. So if the system had crashed or restarted for us, that would have been okay. Or if it dropped down to handle 0 requests, that also would be okay because we get alerts in those instances. What actually happened to us here was it dropped down and handled very, very little traffic. And at the time, we didn't have an alert set up for that. When we looked at the system and it got into this state, we found tens of thousands of messages all queued up in the ZMQ process's mailbox. So you have to remember that this is one single process with an active socket. So any request coming in from the ad server, the request immediately puts a message into the mailbox of the ZMQ process. Since the ZMQ process is also sending responses back, the mailbox is full of both requests coming into the system and also responses which had to be sent back out to the ad server. Add on top of that then, when we send a response back, there was a selective receive statement, so we had to block for a little bit of time to do that. And yes, we had other applications running on the same host because we thought this system is so great, it doesn't matter how many applications we have running on the server. So that looks pretty bad, and how did we fix it? Well, this happened fairly early on in the days for us, and actually fixing it wasn't the first issue we could think of. The first thing we could think of is, before we understood what the problem was, and you have to remember we were C++ developers trying to develop an Erlang system, before we could really understand the problem, we had to make sure that if it happened again, that we didn't have an outage for 1.5 hours. So we created an E script, and this E script was doing RPC calls, checking the message queue length of the ZMQ process at intervals. And then if we saw that message queue was growing, the E script called Erlang halt, that shut down our system, and the halt process restarted it. So it gave us a little bit of breathing space that we could restart the node if it got into trouble. Eventually, as we got more information about what was going on, we came up with different strategies to fix it. What we did for quite a long time then was run the ZMQ process at high priority. So I've heard it mentioned that it's maybe not a good idea to change priorities on your processes, but this is a process right on the edge of our system, and whenever a request came in, we had to change that message in the mailbox into an Erlang process as soon as possible. Because Erlang, as you know, can handle thousands of processes, but if your system has thousands of messages queued up, it's just going to suffer from really bad latency. What we've done lately then was change our active socket into a passive socket. We're polling now for we're polling the ZMQ driver now to see when there are requests there. This also gives us some back pressure we can apply to the ad server, because if we're not taking those requests out of the queue fast enough, the ZMQ will reach its high water mark. And eventually, the next improvement we made was adding multiple ZMQ endpoints. So now it's not a single process that's running in the system, and with configuration, we can increase or decrease the number of processes running there. Another good lesson we learned then was to pool resources. So as I've talked about, we have lots of these different auction processes in the system, all making requests to Couchbase. The connection to Couchbase and all the requests were done by a single process running RLMC. This again actually worked quite well for a certain amount of time, but when that ratio of the one RLMC process to hundreds of these auction processes grew to a certain threshold, the system again had a lot of latency in it, and the message queue kept building up in the RLMC process. So to fix this, we created a pool of those RLMC processes. And now we've changed the ratio to, for one RLMC process, we have one auction process. So there's no starvation of a single RLMC process trying to run on the CPU. The only thing new in this system here now is that the auction process has to choose an RLMC worker. And we wanted to choose the RLMC worker that's been idle the longest possible time. To do that, we basically want to round robin through the RLMC processes. What we've done for this is store a reference for the process identifier in an ETS table. So this is a representation of that table. And we can see for each RLMC process, we have an index value. So if we know the index, then we can simply find out what RLMC process is there. In order to do this round robin, we need to know the pool size, which is a value n in this case, and we also need a value for index. So if index value is 1, we look up the table at index 1 and we get process 0, 100, 0. And this is the code that we use to look up the table from the auction process. It first gets a pool size at line 2, and then it uses update counter to get that index, and then it's just a lookup element to get the process identifier for the RLMC process. So at line 3 we use update counter because as well as getting a value for the index, it's also updating the value in the ETS table atomically. So we're guaranteed that when auction processes go to lookup index, they're always getting an incremental value. Let's update counter works great, and I've seen it mentioned in a lot of different places. There are some times though that you don't need to round robin through your resources. So another solution we use as well is Erlang p-2. Erlang p-2 takes an Erlang term as the first argument and an integer as the second. And what it does is hash that Erlang term into an integer value in the range of 0 to the pool size. So because in this case it's a DSP process calling at the process identifier of self is different each time it's called, and we can get a random value of index. To compare the two, update counter is useful whenever you want to round robin through your resources. But p-2 can be used if a random selection is good enough. We found p-2 to be about 1.5 to 2 times faster, and since p-2 doesn't have to write or update an index value, there can't be any locking in the system as well. So tracing and debugging is another good thing we want to exploit on the system. Just recently we had a spike in one of our timers, and this timer is called the bid collection time, and it represents the time that the auction process will wait to get all the responses back from all the DSP processes. So what we found was every 20 to 30 minutes we would get this massive spike, and it's about 5 times the value of what we would expect this timer to be. And it did happen when the system wasn't really under any load. We looked at the code and we couldn't really figure out what was happening there either. And this wasn't a prolonged outage, so we couldn't log on to the system and do some printouts from the shell and check what was going on. So in fact, we're talking about for a few milliseconds, we got one particular spike. It's the only possible way we could think actually to figure out what was happening is use the trace system in Erlang. So what we did was decide, okay, let's turn on tracing for all new processes being spawned in the system. So we use dbg tracer for this. We give it a callback function called trace handler. So a tracer process gets started up, and it's going to use trace handler for a callback. Trace handler then gets some state, which is a tuple. And in that tuple, we're given it IO, which is a reference to a file we're going to write information out to. It's given an empty dictionary, and this dictionary is going to be useful for storing information about processes. It's been given threshold, threshold represents the value of the timer. So if we reach threshold, we definitely want to have information logged to I/O. And count value was just for safety. So if trace handler was called more than count number of times, we just wanted to shut down the trace system in case anything was going wrong. So line 2, we got the process identifier of the tracer, and then in line 3, we enabled tracing on function calls with timestamps enabled as well. So the next thing we had to do after we turned on tracing was decide, is the process going to be used for an auction or not? In our system, we know every process that's going to do an auction is going to call the function bid processor process request. So we turned on this particular trace pattern. If bid processor process request got called, it meant we wanted to dynamically enable more detailed tracing. So this is one of the function clauses for trace handler where bid processor process request is called. In line 2, we turn on the more detailed tracing. So we again enable tracing with timestamp. We trace messages being received into the process. We trace function calls. We also trace when the process gets scheduled in and out by the scheduler. And for each of these events that we have enabled tracing on, we have to add another function clause to trace handler. And all the function clause is doing is similar to line 3 there, which is put a key value into that dictionary where the key is the process ID and the value is the timestamp and all the information about the event that has just happened. So another thing we did then was put on a trace pattern for the function which is logging the value of the timer. And if we found the value of the timer was greater than threshold, we decided, yes, it's time to dump all that information about that process into the file. So conclusions from this are that it's a real-time bidding exchange is a nice concurrent system, but in our experience we found the hard way that single processes are bottlenecks for your Erlang system. The way we approached those bottlenecks was to set either the process to high priority, which might not be suitable in every case, but also a more common way to handle bottlenecks is to have process pools. We've also seen as well that the Erlang VM is a great platform for debugging issues. For the future for us, we hope to continue to scale the system now with more publishers and more demand partners. We're continue to build a great Erlang team in Dublin and elsewhere. So far, it's been a great team to work with. There's been a lot of knowledge sharing about Erlang, and people are really enthusiastic to build their knowledge of Erlang as they work with it. AOL in Ireland is trying to support the Erlang community as much as we can. So we offer internships to graduates, and we have a graduate with us at the moment who is contributing to our Erlang platform. We also do some presentations going around universities, and we present to undergraduates who are just interested in learning new technologies in general. And then in Dublin, in September, we will host our second Erlang factory at the AOL Ireland headquarters in Dublin. So if any of you guys are available or want to come, you'd be very welcome. So I've left some time for some questions at the end, and thanks for your attention.
When you came into this problem with the active one process, did you try passive active ones?
Yeah, with the driver, if active once had been available, we would have used it. So it's not JNTCP we're using there; it's a ZMQ driver. So yeah, active once would be something that we would probably like to move towards, because having the passive socket there, we we're using a lot of CPU, even when the system is not too busy, just polling for that socket. So it's probably something that's still going to evolve at some point even more. Something like active once would be good for us, yeah.
It's possible that I missed it, but what was the time spike? What was the cause of it?
Sorry, yeah. So the cause of the timing spike, well, it was actually to do with a very bespoke integration with a particular demand partner we had. What we were suspicious about was there something special about this demand partner that we were getting requests back very late. And we thought, well, it's impossible to happen because we have timeouts waiting for responses back. So we thought either the timeouts aren't working, or the Erlang scheduler is maybe not working here, or there's just something wrong with message passing that is very slow. The actual cause was, although the timer was called the bid collection time, the problem was actually sending the request, not waiting to get a response. When you're sending a request, we had to make a request to another gen server, so another bottleneck. And it just so happened that this gen server, from time to time, had to make requests to DNS. And if that request to DNS was ongoing at the same time, the gen server blocked. And this was actually giving us a spike. So, yeah, that's what it was.
From your original diagram about where the request comes from, in terms of that's me pressing something on the keyboard that requests a page, what I'm unsure about, and perhaps others are, is why does it go to AOL? Are these just using AOL as an ISP?
No, it's not to do with the ISP as such. It's to do with publishers who want to use an ad serving platform. So publishers could go to a number of different ad serving platforms. So probably familiar with Google and companies like that. So if they've decided to go with AOL, then in the markup you receive back from their web browser, the HTTP request goes to ad server rather than anybody else's ad server. So it's just it's a business arrangement between the publisher and AOL, and that's why the request is coming to us.
How much money does each request generate?
Yeah. So, of course, everybody wants to know that answer. It's okay. I'll just be very generic here. Typically, to get an ad served on a publisher's browser, we could be talking about less than a cent actually to get that displayed. Now, it can vary. It can depend if that publisher's using real-time bidding. The platform also supports a private marketplace where there's direct deals between publishers and advertisers as well, which I haven't really talked about here. Those can be valued a bit more. But typically, yeah, the publisher's only getting less than a cent for the ad, and then they're giving us a tiny piece of the tiny piece that they got. So yeah, the only way for the system to possibly make money is to do as many concurrent requests as possible. You could scale it quite easily, one request per server, but yeah, you have to do thousands of them really for it to start paying.
So what kind of latency requirements do you have on a request?
Yeah, so it's a good question. We have, so our latency requirements come between the ad server and the RTB Exchange. So the ad server doesn't want to wait too long to get our response back. However, RTB Exchange has to send a request over the internet to the DSPs. So we give DSPs SLAs, and typically around the value, and we're talking hundreds of milliseconds rather than tens or single digits of milliseconds. So it's 100 milliseconds plus kind of latency agreements we have with the ad server, and the actual latency we would have, latency requirements we have at the moment could change tomorrow. It just depends on the business side of the organization. Do they want to decrease that latency, or can they live with a longer latency? If they can wait a little bit longer to get an ad displayed, it probably means there's going to be more demand partners who got the opportunity to respond back into an auction. So there's a balance between waiting a long time and making sure you get all the bids back as well. So, but yeah, we're talking hundreds of milliseconds, but it can depend on a publisher by publisher basis as well.
Okay, I've got one question. From an Erlang beginner's point of view, what's the one tip you can give to people who are beginning with Erlang in order to build a massively scalable concurrent system? What is one thing I should do, and then what is one thing I should avoid doing at all cost?
Good one. I think we totally rely, when you're building a system like this from scratch, actually scalability looks like a problem. Another problem is requirements which keep coming into the system from product organization, and which can continually change depending on how the business is going. So test-driven development is actually my advice to anybody who wants to build a system like this. And then when it comes to scalability, well, put it into your load test system and see how it scales. You can always change it, so long as it's a testable system that you developed.
Right. Please give it up for Philip Clarke from AOL.
Thank you.